Howdy, folks, and welcome back. Hope you're all blessed and doing okay out there. Well, for today's video, I present to you evolution of the air brake. An air brake is a very important braking device on trains, semi-trucks, and buses. It makes stopping a lot safer than regular brakes. This program is amazing, educational, and was presented by the Wabco Company and I think the Westinghouse Company as well. Anyway, I'll quit yakking and let the program do the talking. Here we go, and all aboard for evolution of the air brake. Dang, things not straight.
For well over 100 years, the Westinghouse Air Brake Company has been a trailblazer in the field of air brake technology. Innovative braking products that have opened the doors of progress in railroading. Time and time again, new Wabco products have solved problems, removed barriers, and led the way for major advancements in railroad productivity. This leadership continues today with new product breakthroughs to better meet the ever-changing needs of the railroad industry across the North American continent. The purpose of this video is to help bring about a better understanding of the functions of the air brake system, from its early beginnings to the present day. In order to accomplish this, we must first take a look back at the problems which confronted the railroad industry during the past century and examine the remarkable track record of problem-solving innovation that has always been the Wabco tradition. The biggest problem facing the fledgling railroad freight industry in the early 1870s was trying to find a safer, more efficient way of slowing down and stopping hundreds of tons of rolling stock traveling on steel rails. At that time, brakes were manually applied on moving trains. The operation was quite simple. When the engineer wanted to slow down or stop the train, he would blow the whistle in the locomotive, alerting the brakeman to move from car to car, turning the cranks, which would operate a series of levers and push rods and force the brake shoes against the wheels of the cars. Needless to say, these early brakemen needed strong backs, agile feet, and a lot of luck to survive this hazardous occupation. This early crude method of braking also placed severe restrictions on the length and weight of train consists. In an effort to provide a more reliable means of applying brakes on moving trains, the freight railroad industry turned to the Westinghouse Air Brake Company, whose founder, George Westinghouse, had developed and manufactured a device known as the straight air brake in 1869. The basic principle of this first air brake was quite simple. An air pump installed in the engine was used to compress air to 50 to 70 pounds per square inch, which was then stored in a main reservoir. The reservoir was piped to a three-way cock, which acted as the engineer's brake valve. When the engineer wanted to apply the brakes, he simply opened the valve to permit the air to flow through the pipes and flexible hoses installed between the cars and into the brake cylinders on each car, forcing the pistons out, and through a series of rods and levers, pushing the brake shoes against the wheels. To release the brakes, the engineer placed the three-way cock into the release position, which allowed the brake pipe and brake cylinder air to exhaust, thus releasing the brakes. Although the straight air brake was notable for its simplicity and was quite an improvement over manually operated brakes, it had two major drawbacks. First, the system was not fail-safe. Even though Westinghouse had the foresight to develop a glad hand hose coupling, complete with a check valve that would close off the airflow in the event of a train separation, the back end of the train would have no air supply to apply the brakes in the event of a separation while the brakes were in the release position, as would be the case when climbing a grade. Should such a breakage occur under this condition, the hand brakes would have to be used to stop the cars behind the brake-off to keep it from rolling down the grade. The second shortcoming was the response time required to apply and release the brakes on long trains, that is, trains hauling more than 6 cars. By its design, the air flowing from the main reservoir would be used to apply the brakes hard on the engine, tender, and first car of the train before much brake was applied to the cars in the rear of the train. Thus, the rear end of the train, in which the brakes were not fully applied, would drive into the front end of the train, where the brakes were fully applied. The situation would be reversed when the brakes were released, as the brakes on the front end of the train would be fully released when the brakes on the rear end hung on, causing excessive pulling between the cars. These problems were solved with the introduction of the first automatic air brake in 1872, which added a triple valve and auxiliary reservoir to each car. With this system, the engineer would charge the brakes by opening the brake valve and permitting air to flow from the main reservoir through the triple valve and into the auxiliary reservoirs in each car. To apply the brakes, the engineer would make a reduction in brake pipe pressure using the locomotive brake valve. The triple valve on each car would then close off brake cylinder exhaust and allow air to flow from the auxiliary reservoir into the brake cylinder. This system also had a very important fail-safe feature. If the train would separate or a brake pipe hose should burst, the triple valve would recognize this as a reduction in brake pipe pressure and would automatically apply the brakes in the same manner on both sections of the separated train. The first known application of the automatic air brake in freight service was made to cars on the Eastern Kentucky Railway in August 1877. In addition to saving many lives and averting serious injuries, the new brake system also led the way to increased productivity by allowing increased train speed and longer train consists. The new problem was too much slack action on trains hauling more than 20 cars. Remember that slack action is caused when the brakes are applied at the front end of the train before the rear end of the train, or released at the front end while holding on the rear end. A faster means of transmitting the air throughout the system was needed to alleviate this condition. The severity of the slack action problem was dramatically accentuated during the first of the famous Burlington trials held in 1886. The violent nature of the slack run-in and shock that occurred on the 50-car test trains and the threat of costly damage to the freight cars used in the testing forced a premature ending to the trials that year. During the trials in 1887, George Westinghouse developed the quick-action triple valve by totally redesigning the existing triple valve using larger internal parts and air passages. The diameters of the brake pipe and fittings were increased from 1 inch to 1 1/4 inch. With this new arrangement, the emergency transmission speed of the air was accelerated to the point where the brakes on the 50th car began to apply in approximately 6 seconds. In less than a decade, the number of cars being hauled by locomotives grew from 6 to 50, thanks to the innovative developments of the Westinghouse Air Brake Company. But as the demands for even longer and heavier trains increased, so did the problems of effective train control. Again, WABCO came to the forefront with the development of the K triple valve, introduced to the industry in 1907. The main feature of this valve was the quick service function, which permitted some of the brake pipe air to flow directly into the brake cylinder of each car. This created a serial action, whereby the control valve on each car helped to transmit the signal to the next car throughout the length of the train. This increase in transmission speed led the way to higher tonnage cars and train lengths of up to 80 cars. During this period of growth and development in the field of air brake technology, however, other drastic changes were taking place in the rail industry, which led to more train control difficulties. The typical ore cars of the early 1890s were made of wood and carried a 25-ton load capacity. Around the turn of the century, these cars gave way to the all-steel 50-ton capacity hopper cars. And by the mid-1920s, 55 and 70-ton capacity coal and ore cars were common. And 100-ton capacity hopper cars were beginning to enter the railroad scene. Not only were these higher capacity steel cars heavier, they also were longer, which increased brake pipe length throughout the train consist. Soon, the old problem of slack action reappeared, compounded by the problem of poor release on trains over 80 cars long. Again, Wabco led the way with the development of the AB control valve, a major milestone in the evolution of the air brake and the forerunner to our modern-day freight brake control valve. Introduced to the industry in 1933, the AB valve was comprised of a pipe bracket, a service portion, and a separate quick-action emergency portion. A two-compartment combined auxiliary and emergency reservoir was used with this new equipment. The emergency portion provided a positive higher emergency brake cylinder pressure at a uniquely controlled rate to control slack action. Emergency transmission speed, which had been approximately 680 feet per second with the K valve, increased to approximately 930 feet per second with the AB valve. A serial action accelerated emergency release function was furnished to speed release and recharge following an emergency brake application on longer trains. The service portion of the AB valve provided an even more dramatic improvement in transmission speed. Where the service transmission time for the K valve had been approximately 125 feet per second, the quick service feature of the AB valve quadrupled this transmission speed to 500 feet per second. In simple terms, while the K valve was satisfactory for trains of 80 to 100 cars, which required 4,000 to 5,000 feet of brake pipe, it was not adequate when brake pipe lengths began to increase. Thanks to Wabco technology, it was now possible to safely operate and control 150-car trains with brake pipe lengths of up to 7,500 feet. The AB control valve was standardized by the Association of American Railroads in 1936 and contributed immensely to the growth of the railroad freight industry for the next quarter of a century. It was not, however, the final solution to the industry's train control problems. In the early days of railroading and up until the middle of the 20th century, brake shoes were made of cast metal. Those who are old enough probably still remember the distinctive squealing sound caused by the cast iron metal shoes being applied to the steel wheels of the freight trains in the 40s and early 50s. Perhaps this is where the term coming to a screeching halt came into being. Doesn't take much of an imagination to envision the problems created by this situation, ranging from excessive wheel and brake shoe wear and hazardous sparking conditions to an inordinate amount of vibration throughout the entire brake rigging and car underframe. To alleviate these problems, Wabco, the worldwide leader in the development of air brake technology, entered into the field of friction composition brake materials and helped to pioneer one of the most significant developments in the evolution of railroad braking, the composition brake shoe. In 1954, the Railroad Friction Products Corporation was formed. This new company introduced the first successful high-friction composition brake shoe to the railroad industry. The shoes were introduced under the brand name of Cobra, an acronym for composition brake, and won widespread approval of the industry in a very short time. Some of the obvious benefits derived from the use of the Cobra brake shoes were improved wheel performance, increased shoe and wheel life, and the elimination of brake shoe sparking. Other more subtle benefits contributed enormously to improved railroading efficiency and productivity. These included improved braking performance, particularly by increasing friction brake effectiveness at higher speeds, reducing the braking forces required to generate retarding force, thereby downsizing equipment size and air consumption. More uniform friction, which permitted a running release, enabling increased efficiency for loading and unloading coal and ore trains. And last but not least, the Cobra shoe finally brought a quiet end to the screeching halt. Although the Cobra high-friction composition brake shoe was a major advancement in the application of braking force to the wheels of the freight car, the foundation brake rigging, which was used to apply the shoes to the wheels, had remained relatively unchanged for more than 60 years. This conventional rigging was comprised of a series of levers and rods which required numerous pin connections and was actuated by a brake cylinder which was mounted to the car body. Then, in 1958, the Westinghouse Air Brake Company introduced a truck-mounted direct-acting brake assembly to the railroad industry. The Wabcopac brake assembly differed from conventional rigging in that it was installed within the confines of the car trucks and combined the functions of the brake cylinders and brake beam into one unit. By transmitting braking power to the trucks pneumatically rather than mechanically, this system eliminated anywhere from 10 to 20 of the pin connections, along with the many rods and levers required on a typical conventional brake rigging. The beam-mounted cylinders provided a highly efficient direct-acting braking force, which was much more uniform than conventional rigging, and generally improved wheel life. Wabcopac also led the way to simpler car design by eliminating the need for a body-mounted cylinder and much of the extraneous hardware associated with conventional brake riggings. While these developments were taking place, another major braking problem cropped up in the late 50s and early 60s with the inception of the longer piggyback and container freight cars. Whereas the standard freight cars generally required 50 to 70 feet of brake pipe, this new breed of cars extended brake pipe lengths to 90 and even 100 or more feet. Train brake operations on consists containing a significant number of these specialized cars showed slow and sluggish service brake response due to the increase in brake pipe length and volume. There was also concern that the emergency signal might not carry through the train if the control valves on 2 or 3 adjacent cars were cut out due to problems on the road, which could lead to severe in-train forces and inadequate braking. To alleviate this condition, Wabco developed the A1 reduction relay valve to assist the quick service function of the AB control valve. The A1 is comprised of a B1 quick service valve and a number 8 vent valve. The AAR soon mandated that this function be added to all cars requiring more than 75 feet of brake pipe length. Yet another extremely significant air brake development occurred in 1962 when Wabco introduced the ABD control valve to the railroad industry. Like its predecessor, the AB valve, the ABD valve consisted of a service and emergency portion which were physically compatible with the AB pipe bracket. Diaphragm-operated pistons replaced the metallic rings used in the AB valves and provided more consistent and reliable operation for a longer period of time without a tension. The cleaning period, which had been 4 years for the AB valve, was essentially doubled with the ABD valve. A new accelerated service release function allowed running brake releases to be made in long consists without pulling apart the train. Overall, the ABD valve contributed to more flexible and efficient train operation. The ABD was made alternate standard by the AAR in 1967, but the demands being placed on the railroad industry for even more productivity had still not reached its peak, and neither had Wabco. In the early 1970s, heavier trains were requiring longer stop distances, and Wabco engineers were working longer hours to develop an even more sophisticated control valve to handle the high-tonnage freight cars of that era. Another major step in the evolution of the air brake was realized in 1974 when Wabco began production of the ABDW control valve. Although the ABD service portion remained unchanged, the modifications made to the emergency portion in the new ABDW valve proved to be highly beneficial to the service braking performance of the complete valve. An accelerated service application valve was mounted to the exterior of the ABDW emergency portion. This AAV portion provided a continuous quick service function, which reduced the time required to completely develop a full service brake on long trains by almost 50%. This in turn shortened the full service brake stopping distances by 15 to 20%. The maximum practical train length was increased from 7,500 feet with AB and ABD equipped trains to 10,000 feet with ABDW equipped trains. The ABDW valve allowed cars with up to 100 feet of brake pipe to operate without a B1 quick service valve and provided faster service applications when applied to short, medium, or long cars. The ABDW valve was standardized by the AAR for all new and rebuilt freight cars in 1977. As you can see, WABCO technology has played a significant role in the growth and well-being of the railroad industry for more than 120 years. And we don't plan on slowing down now. Challenges confronting the railroad industry in the future will be quite different from those of the 1970s and 1980s. Car utilization is improving, and fewer freight cars are hauling heavier loads while running more miles. Cars are being designed for gross rail loads of up to 286,000 pounds, and yet empty car weights are becoming lighter. Some empty car weights are as low as 16% of the fully loaded car weight. As a result, the need for efficient, flexible, and reliable brake systems on America's freight trains has never been greater. Brakes on today's high-mileage cars incur more applications and related wear and tear than was experienced on the average freight car in the past. Increased rubber wear and fatigue, along with increased mechanical wear, may result in internal leakage within a time frame far shorter than that previously encountered. One form of leakage from wear and fatigue may allow brake pipe pressure to leak through the control valve to the cylinder during sustained light service brake applications made on long grades. This can cause brake cylinder pressure on the affected car to rise, causing higher brake forces and overheated wheels when the car tries to contribute more than its fair share of the total train braking effort. The AAR has recognized this possible internal leakage and beginning in 1993 has mandated a new 90-pound single-car test designed in part to detect internal control valve leakage. WABCO's new ABDX valve is designed to significantly improve protection against such internal leakage. This type of leakage will be far less likely to occur on ABDX-equipped cars because the quick service limiting valve and service graduating valve designs are improved to seal better and last longer. As we have discussed, heavier car weights and the resulting increasing train tonnage have presented a continuing challenge for train operations and brake systems. Today's heavy haul trains can weigh up to 20,000 tons. Control of stop distances and train slack action on these heavy haul trains is more demanding and more critical than ever. WABCO's ABDX and ABDXL valves are designed to optimize service brake application response time on both standard and very long freight cars. ABDX and ABDXL valves are significantly improved in both quick service and continuous quick service or accelerated service application functions. The most significant gain was accomplished by incorporating the continuous quick service function into the emergency slide valve. This feature represents a major improvement over the ABDW valve, where the function is performed by a separate and more complicated accelerated application valve portion attached to the emergency portion. The precise, smooth functioning ABDX valves are able to improve brake application response times by more than 20% over ABDW valves and by more than 60% over ABD valves. This higher application speed can significantly shorten service brake stop distances or accomplish the same stop distance using lower braking forces. Because effective brake application speed is controlled primarily by the speed at which brake pipe pressure is reduced in the entire train, ABDX valves will help all older style valves in the same train perform better. The result is that each car still does only its fair share of the overall train braking effort, but does it better. High-capacity cars are creating increasingly heavier trains with harsher in-train forces and related train slack action. Severe slack action during the service brake applications and resulting train line pressure fluctuations are now suspected by the AAR to be the most frequent cause of undesired emergencies, and undesired emergency brake applications are a major cause of train delays. ABDX valves are stabilized to minimize undesired emergency brake applications from being triggered by such pressure fluctuations, and by doing so, reducing the related stress on cars and their wheels. ABDX control valves clearly offer improvements which will better assure reliable, uninterrupted freight train operations. WABCO has not simply designed and introduced the new and improved control valve, however, and disregarded all prior vintages of valves. Through the judicious application of ABDX technology, WABCO is now equipped to upgrade ABD and ABDW valves to include some or all of the ABDX features. These include stabilizing the emergency portion to reduce UDEs, replacing the quick service limiting valve and service graduating valve with new designs to improve internal leakage protection. Through these innovative programs, WABCO has in essence provided today's railroads and car owners with an upgradable or renewable resource. Empty load equipment, in one form or another, has been used on some freight cars since early in this century. In modern day usage, empty load equipment is applied to reduce braking forces on empty cars having light weights of less than 22% of maximum capacity weights in order to meet AAR braking ratio requirements. WABCO's SC1 empty load equipment has been the industry standard since 1965, with more than 70,000 car sets in successful service. SC1 equipment consists of three components: the S1 sensor, the P1 proportional valve, and a volume reservoir. The S1 sensor valve measures truck spring deflection and functions with the proportional valve to reduce brake cylinder pressure on empty cars to 60% of the loaded car pressure by causing a portion of the air to flow into the volume reservoir. Unlike other designs, SC1 equipment does not lock up, but permits some correction of improper brake applications that may be caused by dynamic car motions due to unlevel track conditions. As the car rolls to level track, an improperly applied loaded brake on an empty car can therefore be reduced to prevent over-braking and minimize wheel sliding. WABCO's new ELX empty load equipment has the additional feature of reducing empty car brake forces inversely proportional to higher brake pipe pressures, while also offering a more proportional brake for intermediate weight loads as experienced on intermodal cars. As we have learned, higher brake pipe pressures cause higher brake cylinder pressures and related higher braking forces. A 40% reduction in brake cylinder pressure on a train running with 100 or 110 psi brake pipe pressure may still produce too much brake force on an ultra-lightweight car. With ELX, brake cylinder pressure would automatically be reduced by about 46% on an empty car during a 110 psi emergency application, ensuring optimum braking forces under most conditions and with self-correcting features similar to the SC1 equipment. The primary purpose of a freight car empty load brake is to minimize the potential for wheel sliding when heavy braking is done on empty cars. and the ELX empty load equipment is designed to achieve this in a highly reliable manner. Earlier in our video, we have examined the complexity of conventional freight car brake rigging, which uses a series of rods, levers, and brake beams to transmit brake cylinder forces through a slack adjuster to the wheels. The basic concept, with the exception of the automatic slack adjuster, has changed very little from the early days of automatic air brakes. During recent years, however, standard body-mounted brake rigging installed on ultra-lightweight cars have been found to cause increased braking forces on curves, causing sliding wheels and resulting wheel damage. We have also seen how the truck-mounted Wabco-Pack brake assembly provided a successful alternative to conventional brake rigging in the early 1960s. More than 200,000 freight cars have entered service with Wabco-Pack since that time, and many of these cars have been upgraded to Wabco-Pack 2. Wabco-Pack brake units made it possible for the industry to build a variety of new car designs that did not lend themselves to conventional brake rigging. Today, Wabco's new TMX truck-mounted brake equipment offers all of the advantages of Wabco-Pack 2, including easy installation, even shoe force distribution, integral universal slack adjuster, and simplified handbrake hookup, plus the additional advantages of accommodating 2-inch composition brake shoes, replaceable brake heads, and at least 500 pounds less weight when compared to conventional brake rigging. TMX, working in unison with ABDX control valves and, if required, ELX empty load brake equipment, will meet the performance needs of today's most demanding freight car service, with a long-lasting brake system that will provide reliable service with optimum wheel and brake shoe wear. A very substantial cost savings can be expected because the freely suspended TMX arrangement overcomes the tapered shoe wear that is characteristic of other truck-mounted brake assemblies. TMX can also improve wheel wear by reducing wheel flange wear and curve effect braking force increases caused by conventional body-mounted brake rigging. Wabco products continue to push the state-of-the-art for railroad braking systems by offering improved performance and reliability for tomorrow's railroad needs. More than ever, the Westinghouse Air Brake Company continues to be a name you can depend on for all your air brake needs. Wabco, leading the way into the 21st century.
Wabco presents the evolution of the air brake, Part 2, Locomotive Brake Equipment. In the early days of railroading, before the invention of the air brake, the locomotive engineer had very little actual control over stopping his train. His primary responsibilities were to keep the train moving, maintain a close watch on the track ahead for any obstructions or damaged rail, and signal the brakeman when it was time to apply the brakes by hand. He would then sit and wait until the train came to an eventual stop. All of this was about to change in dramatic fashion on a notable April morning in 1869, when an engineer by the name of Daniel Tate left the Panhandle station in Pittsburgh at the controls of the first train ever equipped with air brakes. Aboard the train were several important railroad officials, accompanied by the youthful inventor of this mysterious new brake, George Westinghouse. As the train passed through Grant's Hill Tunnel, an unsuspecting farmer was heading toward the marketplace in a horse-drawn cart laden with produce. Tate's train was about midway through the tunnel as the farmer's horse trotted onto the wooden railroad crossing and stopped dead in its tracks. Seeing this, Tate's first instinct was to blow the whistle to alert the brakeman. The horse panicked at the sound and began to buck wildly. Tate then grabbed the handle of the strange new device piped into his locomotive cab and pulled as hard as he could. Almost instantaneously, the sound of air rushing through the pipes was followed by the shrill, screeching sound of the cast-iron brake shoes being forced against the steel wheels of the tender and trailing cars. History was made that morning as the locomotive stopped just a few yards short of certain disaster. The first successful air brake application had been made. A new age had begun. The basic principle of that first air brake was quite simple. An air pump installed in the engine was used to compress air to 50 to 70 pounds per square inch, which was then stored in a main reservoir. The reservoir was piped to a three-way cock, which acted as the engineer's brake valve. When the engineer wanted to apply the brakes, he simply opened the valve to permit the air to flow through the pipes and flexible hoses installed between the cars and into the brake cylinders on each car, pushing the pistons out and through a series of rods and levers, forcing the brake shoes against the wheels. To release the brakes, the engineer placed the three-way cock into the release position, which allowed the brake pipe and brake cylinder air to exhaust to atmosphere, thus permitting the release spring to force the piston back into the brake cylinder. Although the straight air brake was quite an improvement over manually operated brakes, it had two major drawbacks. First, the system was not automatic. In the event of a train separation while the brakes were in the release position, as would be the case while climbing a grade, the handbrakes would still have to be applied to the cars behind the brake-off to keep them from rolling out of control. The other problem was response time on longer trains, that is, trains made up of more than 6 cars. Since the air was transmitted to each car from the main reservoir up in the locomotive, the brakes would be fully applied to the first few cars of the consist before much air could be applied to the cars in the rear of the train, causing the cars in the rear to run into the cars in the front. The situation would be reversed when the brakes were released, as the brakes on the front of the train would be fully released while the brakes on the rear of the train hung on, causing excessive pulling forces between the cars. These problems were solved with the introduction of the first automatic air brake in 1872, which added a triple valve and an auxiliary reservoir to each car. With this system, the engineer would charge the brakes by moving the brake valve handle to the first position, which would allow the compressed air to flow from the main reservoir into the brake pipe and flexible hoses, and through an open port of the triple valve into the auxiliary reservoirs under each car. Once the system was fully charged, the engineer would move the brake valve handle into the second or running position, thus closing off the airflow between the main reservoir and brake pipe line. To apply the brakes, the engineer would move the handle to the right, which would gradually vent brake pipe air to atmosphere through an exhaust port in the brake valve body, thus reducing brake pipe pressure. This drop in brake pipe air pressure causes the higher pressure air in the auxiliary reservoir to flow into the triple valve, moving the piston and slide valve and permitting the air to flow into the brake cylinder, where the piston would be forced out and the brakes would be applied. The brakes could also be applied by venting brake pipe air at any of the conductor's valves located within each passenger car. This concept of applying brakes by reducing the air pressure was significant in that any reduction in air pressure automatically applied the brakes. This meant that if a brake pipe hose would burst, or if the train would become uncoupled for any reason, the brakes would be applied on both sections of the separated train. The three-way cock evolved into the first automatic brake valve in 1881. This valve marked the introduction of the rotary valve, which controlled airflow to charge brake pipe. It also employed a balancing spring to control brake pipe reduction. An interesting feature of this valve was the early appearance of the notched quadrant, which indicated the various handle positions. Further improvements were made in 1886 with the introduction of the feed valve, which regulated brake pipe pressure to a constant level, and the equalizing piston and externally mounted equalizing reservoir, which provided the engineer with an automatic brake pipe reduction feature. With this feature, once a desired reduction is made in the equalizing reservoir, the brake pipe air pressure in the trailing cars automatically reduces by the same amount. Note that although this reduction time may vary due to the condition of the brake pipe and the length of the train, because this reduction was automatically monitored and adjusted by the equalizing piston, the engineer needed only to concern himself with the reduction as indicated by the equalizing reservoir gauge. Here's how the new equipment worked. The engineer charged the system by placing the handle into the release or charging position. Air flowed to brake pipe and through the triple valves, charging the reservoirs on each car. Air also flowed through the equalizing piston chamber, charging the equalizing reservoir. A small amount of air was released to atmosphere through the warning port, which provided an audible warning to the engineer that the brake valve was in the release position. The engineer would watch the air gauges as the system was being charged. The two black pointers, indicating equalizing reservoir and brake pipe pressure, would increase at the same rate until the locomotive brake pipe was charged to 70 psi. The engineer would then place the handle into running position. This closed off the passageways from the main reservoir to brake pipe, equalizing reservoir, and the warning port. At the same time, a port was opened connecting air from main reservoir through the feed valve to brake pipe and equalizing reservoir. The feed valve would regulate brake pipe pressure at 70 psi at the locomotive, while the train continued to charge. When the engineer wanted to apply the brakes to slow down or stop the train, he would move the brake valve handle to service position. This disconnected the passageway from main reservoir to the feed valve, thus cutting off air to brake pipe. It also cut off the passageway between brake pipe and equalizing reservoir. It opened a passageway allowing air to flow from equalizing reservoir to atmosphere, reducing equalizing reservoir pressure at a controlled or service rate. When the desired reduction was reached in equalizing reservoir, the engineer would move the handle to lap position, stopping the reduction of equalizing reservoir pressure. Simultaneously, the equalizing piston automatically reduced brake pipe pressure to the same pressure as equalizing reservoir at a rate no faster than a service rate. The rate of brake pipe reduction on long trains was further controlled by the service exhaust fitting, which prevented the front of the train from applying too much faster than the rear of the train to control drawbar forces within the train. The final handle position was used to make an emergency brake application. The engineer would move the brake valve handle from running to emergency position. This opened a large port from brake pipe directly to atmosphere to start quick action, which then propagated through the entire train. This stopped the train in the shortest possible distance. Equalizing reservoir was also vented to atmosphere during an emergency brake application to reduce equalizing reservoir pressure to that of brake pipe. In another significant development during the next decade, a pipe bracket was added to permit the removal of the operating portion for inspection or repair without disturbing the pipe joints. Although these first brake valves worked fine in the early part of the 20th century, the big high-powered steam locomotives of the mid-1930s needed a more flexible and more sensitive locomotive brake to provide a better match with the performance of the AB-type freight brake control valves, and also to achieve performance required for the new high-speed passenger trains. WABCO provided this match with the introduction of the 8ET locomotive brake equipment in 1934. This equipment synchronized brake cylinder buildup between the locomotive and trailing cars to reduce slack action and permit smoother stops, which was particularly important for passenger service. As freight trains became longer, brake pipe leakage increased and tended to override the action of the brake valve, causing a heavier brake than desired. The 8ET equipment provided automatic control of brake pipe reduction in freight service by means of a first service position on the brake valve. This new position introduced the flat maintaining feature. This was achieved by modifying the equalizing piston and adding a maintaining valve that directed air from the feed valve into brake pipe so that brake pipe pressure would not decrease any faster than equalizing reservoir pressure. In service position, a 20 psi equalizing reservoir reduction from 70 to 50 psi took 10 seconds. The new first service position produced a 6 psi reduction at the same rate, and then reduced equalizing reservoir pressure to 50 psi at a controlled rate over 2 minutes. This feature greatly reduced shocks due to slack action in a long train. In 1941, WABCO came up with another major advancement in locomotive brake control, the 24RL equipment. This equipment featured interchangeable brake valve portions to provide several different combinations which were suitable for all locomotive applications. It was equally effective in the cabs of steam, electric, or diesel-electric locomotives. Even though first service position, which was carried over from the 8ET equipment, gave the engineer better control of his train, something more was required to improve and simplify the handling of trains on descending grades. Until now, the only proven method of controlling trains on long, steep grades was to utilize the retaining valves mounted on each freight car and implement a braking maneuver known as cycle braking, which is the alternate application and release of the brakes. The procedure worked like this. The train would have to stop at the top of the grade to allow the brakeman to move from car to car, flipping the handles of the retaining valves into the retain position. By doing this, the valves retained pressure in the brake cylinders during the release part of the cycle braking, while the auxiliary reservoirs were being recharged. Needless to say, this took considerable time, and in bad weather was an unpleasant and even dangerous task when the cars, tracks, and ground were covered with snow and ice. And once the entire length of the train reached level ground at the bottom of the grade, the train would have to be stopped again while the brakeman opened the retaining valves to the exhaust position. While the train was descending the grade, cycle braking was performed exactly as the name implies. The engineer would move the brake valve handle to the first service position, make a minimum reduction, then move to the running position for a while, then move to the charging position, back to running, and back to first service, and keep repeating the procedure as long as the cars were descending the grade. The engineer performed the task of cycle braking mostly by feel, which usually came about through years of on-the-job experience. But no matter how adept the engineer became in handling the art of cycle braking, the procedure itself consumed large amounts of air and inevitably resulted in uneven braking throughout the train. This problem was alleviated in 1954, when the pressure-maintaining feature was offered with the D24 brake valve. A new equalizing piston portion was designed with a sensitive diaphragm arrangement to maintain brake pipe pressure at equalizing reservoir pressure with filtered air from the feed valve in lap and service positions as well as in first service position. This resulted in less air consumption and more uniform braking throughout the train. It also relaxed the requirement for retaining valve use when descending grades. With the advent of the modern diesel-electric freight power age, however, the 24RL had outlived its broad usefulness. So, in 1957, Wabco came out with a totally redesigned locomotive equipment package built around the diaphragm, O-ring, spool, and poppet valve structure. A simpler design and smaller package significantly reduced the number of moving parts and allowed for a more compact panel-mounted 26C brake valve, as opposed to the cumbersome pedestal mount associated with 24RL equipment. The 26-type brake valve also was adapted for use on various passenger hauling equipment. Brake pipe pressure maintaining became standard. A self-lapping regulating valve was used to control equalizing reservoir pressure proportional to handle position. Today, the 26L equipment is still the common standard for North American diesel-electric locomotives. Although the 26L equipment has remained relatively unchanged, Wabco came out with an alternative to the panel-mounted 26C-type brake valve in 1983. The 30A-CDW is a desk-mounted arrangement which was originally designed for use in passenger locomotive cabs, but is gaining widespread acceptance in the newer comfort cab design freight hauling locomotives. The 30A-CDW is a direct replacement for the 26-type brake valve and provides the same feel as the traditional vertical mount 26C. So far, we've seen how the engineer controls the airflow from the locomotive through the brake pipe and into the various pneumatic devices installed on each car. Now, we'll take a brief look at where the compressed air originates. Wabco has been in the business of designing and manufacturing compressors for more than 100 years. Our present standard offering is the 3CD model, which is a two-stage air-cooled reciprocating type developed primarily for use on diesel locomotives. The 3CD is comprised of two low-pressure and one high-pressure cylinder assemblies, which are used to produce a continuous supply of compressed air, which is stored and maintained in the locomotive main reservoirs. The latest Model 3CD air compressor is designed to be driven by a separate motor, which means it can be operated independent of the locomotive engine, thus saving unnecessary wear to internal parts. The compressor can be operated at speeds of 250 to 1100 RPM and is suitable for service of up to 140 pounds per square inch. A new option now being offered for new and existing air compressors is the 3CD CLA compressor aftercooler, which is used to eliminate much of the moisture from the compressed air before it is delivered to the locomotive main reservoirs. Before we take a look at what happens to the air as it is being compressed, we should point out a few rules of thumb pertaining to air pressure, temperature, and moisture content. Rule number 1. At a constant pressure, warmer air holds more moisture in vapor form than cooler air. Rule number 2. For every 20 Fahrenheit drop in temperature at a constant pressure, the ability of compressed air to retain moisture in vapor form is cut in half. So as the temperature continues to drop, more of the moisture in the air condenses from vapor to liquid form. Rule number 3. As the compressed air is expanded to a lower pressure, its ability to hold moisture in vapor form increases. With these rules in mind, let's trace the flow of air from the time it enters the compressor to the time it is introduced into brake pipe. Air enters the two low-pressure cylinders at ambient temperature. By the time it is discharged after the first stage of compression, the temperature rises to approximately 300 degrees above ambient. The air then enters an intercooler, which acts as a heat exchanger. The cool-down process is aided by cooled air that is drawn over the intercooler fins by a large fan encased in a fan guard funnel assembly. The first stage compressed air is cooled to about 75 degrees above ambient when it enters the high-pressure cylinder, then rises again to approximately 250 degrees above ambient during the final stage of compression. Before the introduction of WAPCO's patented aftercooler, the air would be routed through 60 feet of 2-inch diameter pipe, which served as the only method of heat exchange between the compressor and main reservoir. This has shown to be an inefficient and often ineffective method of alleviating the problem of moisture. By mounting the compact aftercooler directly below the existing intercooler, the air, which remember is discharged from the high-pressure cylinder at 250 degrees above ambient, is now cooled to approximately 10 degrees above ambient. At this point, as we have stated in rule number 2, much of the moisture which was contained in the warmer air as vapor now falls out as precipitated water and flows with the airstream into the bottom of the main reservoir, where an automatic drain valve purges it into the atmosphere. Keep in mind that the air stored in the main reservoir at this point still contains some moisture in vapor form. What is to prevent this vapor from condensing into liquid form somewhere down the brake pipeline? Remember rule number 3. As the compressed air is expanded to a lower pressure, its ability to hold moisture in vapor form increases. Since the air is stored in the main reservoir at a pressure of 140 psi and is expanded to a lower typical brake pipe pressure of 80 psi, the air is able to retain the remaining moisture in vapor form. The result is cooler, drier, safer air, and less chance of brake equipment freeze-ups and malfunctions. Finally, we come to WAPCO's latest entry in the evolution of locomotive brake control equipment, the EPIC 3102. This electro-pneumatic integrated control is designed to replace the industry standard 26L equipment. The EPIC 3102 is based on the use of microprocessor technology to provide electronic logic for controlling the train's pneumatic braking functions. As we have seen, every locomotive air brake system up until now relied strictly on pneumatic logic to control the train brakes. Although pneumatic devices are still necessary to control the brakes, the number of such devices are greatly reduced with the EPIC 3102. Whereas older style locomotive braking equipment could have close to 100 pipe connections, the EPIC 3102 utilizes a compact, self-contained equipment rack that requires only 9 pneumatic pipe connections. The equipment functions are grouped and valve portions are designed so that valve interdependencies are minimized. This streamlined configuration, which simplifies the pneumatic operation, coupled with the enhanced diagnostics built into the EPIC 3102, greatly reduces the amount of locomotive downtime due to testing and troubleshooting. We'll look at the diagnostics in a while, but first, let's go into some locomotive cabs equipped with EPIC equipment. Here we see one of the first locomotives to be retrofitted with EPIC equipment. This particular locomotive was originally equipped with a standard vertical-mounted 26C brake valve. The piping for the pneumatic brake valve has been disconnected, and the automatic and independent valves are removed. The opening for the independent valve is covered with a blanking pad, and in the space previously occupied by the automatic brake valve, we are installing a new device, which we call the cab control unit. The cab control unit was designed to have the same look and feel as existing 26C and 30A CDW brake valves, but that is where the similarity ends. Whereas the 26 and 30 brake valves are strictly pneumatic devices, the EPIC 3102 cab controller units are strictly electronic. Now we'll take a look at how the EPIC cab controller matches up with today's newest locomotive designs. Locomotives and train control have come a long way since the introduction of the first automatic air brake. We should keep in mind, however, that even though equipment becomes more sophisticated and technologically advanced as the years go by, the same basic principles of train braking remain unchanged. We still must rely on a brake valve or cab controller to apply and release the brakes. We still must rely on air gauges of one form or another to monitor the air pressure in main reservoir, equalizing reservoir, brake cylinder, and brake pipe. And we still must conduct periodic clean, oil, test, and stencil procedures to ensure that the equipment is functioning properly, even though the FRA has extended such periods from the mandatory 3 years for pneumatic equipment to 5 years for the EPIC 3102 equipment. And finally, we should keep in mind that no matter how modern and reliable brake equipment is, there will always be situations arising that will need to be diagnosed and corrected. This was one of the main areas of concern addressed by WABCO during the development of the EPIC equipment. We will close out our evolution video with a simple real-time demonstration of the diagnostics built into our EPIC 3102 equipment package, something that we feel is one of the biggest breakthroughs in locomotive braking equipment since the introduction of the 26L equipment more than 35 years ago. This demonstration is being conducted at the EPIC Laboratory located at our Wilmerding Locomotive Products Division facility. We should note that the procedures being performed in this simulation would normally be conducted with a laptop computer from inside the locomotive cab, but in order to provide better visual resolution for you, our viewing audience, we will be using a standard computer and display screen. The first step in our demonstration is to create a simulated malfunction in the system. We do this by disconnecting a wire from one of the magnet valves on the brake cylinder control portion. We then make a brake application so that the malfunction can be diagnosed by the EPIC microprocessor. Next, we call up the monitor and maintenance program and select the fault log from the program menu. The first screen shows that there is data entered in the fault log. By following the command on the screen, we depress the down arrow to view the last entry. The top line on the next screen indicates the malfunction as a brake cylinder reservoir charge timeout error. The message on the next line gives us the corrective measures which must be taken. Since the diagnostics are performed on a modular level, the message tells us to replace the brake cylinder control portion. The next line indicates the numeric value of the fault, in this case a code 7, and also shows the exact time and date that the error was diagnosed. The last line shows the fault category and the time and date when the fault was cleared. Since the fault is still pending, the time-date stamp remains clear. Our next step is to correct the fault. Even though the computer is telling us to replace the module, we know that we could simply reconnect the wire to the magnet valve and correct the problem. But for instructional purposes, we will proceed to remove and replace the brake cylinder control portion. Here we show one of our technicians removing the brake cylinder control portion from the electro-pneumatic laminate. Notice that the lightweight aluminum modules are much easier to handle than the heavier cast iron pneumatic valves associated with 26L equipment. Once the module is replaced, another brake application is made to determine if the fault has been corrected and cleared from the fault log. We then call up the fault log one more time and see that the file is empty, indicating that no current fault exists. To double-check that the malfunction has been corrected, we now move the cursor up to the history log and hit the Enter key. Our display tells us that there are currently 9 entries in the file. Since we are interested in the last entry, we follow the instructions and hit the down arrow. This screen shows that the fault in question has been cleared at the time and date indicated. In the last phase of our demonstration, we show the data being extracted from the EPIC microprocessor and downloaded onto our computer. This information can now be easily transported and made readily available for review by maintenance or supervisory personnel at a later date. We hope that you have enjoyed our program covering the evolution of locomotive air brakes. We would like to point out that every development, every equipment, and every brake valve and cab controller shown in this video was originally designed by the Westinghouse Air Brake Company. Wabco locomotive products continue to push the state-of-the-art for railroad braking systems by offering improved performance and reliability for tomorrow's railroad needs. More than ever, the Westinghouse Air Brake Company continues to be the name you can depend on for all of your air brake needs. Wabco, leading the way into the 21st century.
And there you have it, folks. What a very interesting program. A lot of technical stuff about the air brake system. Now, I'll be honest, guys, I didn't understand all the terminology and all the initials, but I can take a slight guess of like what some of them stood for. Wabtec is still around, so is Wabco. I think the Westinghouse company is still here, and so is Cobra. Although I'm pretty sure since 1994, a lot of the devices and systems have changed and the valves and everything has been completely upgraded, with all new locomotives being built for the railroads today. Anyway, until next time, please be safe around trains. Please like, share, subscribe, and comment. And remember, Jesus is King. Happy rails, guys. See y'all next time.